Let's play some chess! Chess is a complex game, played on an 8x8 board and with a total of 16 pieces per team, grouped into 6 different types. The goal of each team is to capture its opponent's pieces by moving on their tile, with each type of piece having its own possible moves. More precisely, and not considering special cases, you have the pawns, 8 per team, who can only move towards the adversary. You have the rooks, 2 per team, who can move anywhere horizontally or vertically. You have the knights, 2 per team, who move 2 steps in one direction and 1 step orthogonally. You have the bishops, 2 per team, who can move anywhere diagonally. You have the queens, 1 per team, who can move anywhere horizontally, vertically, and diagonally. And you have the king, 1 per team, who can move to any of the neighboring tiles. Putting all of these rules together, you obtain one of the most popular yet complex games of all times. But this is not the game we'll be playing today. Today, we'll be playing random chess. Consider for now the weirdest piece of all, the knight. This piece sticks out from all other ones because of the sensed lack of symmetry in its movements. It moves 2 steps in one direction and 1 step in another direction. For example, when placed here, it can move to any of the 8 highlighted tiles. The game of random chess is then to simply make the piece move around the board by picking the next tile at random from all possible options. Let me now ask an innocent question. If you start from one corner of the board and randomly move around, how long will it take you to come back to that same corner? Naturally, since our movements are random, so is the number of moves it takes us to come back. We could be back in as few as 2 steps or 4 steps, but we could also roam on the board for thousands of steps before finally reaching our origin again. For this reason, we will consider the average return time. Given a set of experiments, what is the average number of moves used to come back to our initial placement? To find the answer to this question, we actually first consider a different problem: the number of visits to each tile. Start again from a corner and consider making the knight randomly move for a large number of steps. While you do so, count the number of times it visits each single tile. Can you try to guess the number of times you visit the corner tile, the middle tile, any other tile? Well, actually, you can. Start with just 2 tiles from the board. For the right tile, the knight can move to 8 different locations. By the symmetry of movements of a piece, this is actually the same as saying that there exist 8 different positions on the board from which the knight can come to reach this tile. Similarly, for the left tile, the knight can go to 4 different locations. And so, 4 different positions can lead to this specific tile. This means that, when moving for a long time across the board, we are 2 times more likely to visit the right tile than the left tile. Moreover, since this number of visits follows the total number of moves made by the knight, it is usually easier to make it into a frequency, dividing the number of visits by the total number of moves. Now, the same argument used for the number of visits applies to the frequency, and we observe that the frequencies asymptotically respect the ratio of 2 we observed when considering the number of possible moves. By considering the number of moves available from all positions on the board, it becomes possible to compute the exact expected frequency on every individual tile. It is then interesting to observe that the frequencies only take 5 possible values, exactly corresponding to the tiles grouped according to their number of possible moves: 8, 6, 4, 3, and 2. Let's now come back to our original problem and see how these frequencies relate to the number of moves it takes to return to the corner. Consider our original corner. Focusing on the frequency of this tile, we see that it is approximately equal to 0.60%. The exact asymptotic frequency is in fact ever so slightly less than 0.60% and corresponds to 1/168. This means that, on average, we visit this specific corner every 168 moves. Well, this is our solution. Indeed, it takes us an average of 168 steps for a randomly moving knight to return to its original corner. Easy enough, no? This method allowed us to find the average number of moves required for a knight to return to its corner. However, the same ideas can actually be applied if we start somewhere else or with another piece. Recall how we obtained the average return time of 168. We first counted the number of moves from each tile. We then added all these numbers together to obtain the total number of possible moves for the knight, 336 here. We then divided all the numbers of moves by this sum to obtain the frequency of visit of each tile. We eventually inverted these numbers to obtain the number of moves it takes to return to our original position. As you can see, we obtained again 168 moves necessary to return to the corner. But we also obtain in this way the return time for all other positions. For example, if we start from a middle tile, then it would take us on average 42 moves to return to this specific location. It is interesting to see that the return time in the center is a quarter of the return time on the corner, since we have 4 more ways to reach a center position than a corner one. Naturally, this method works exactly the same for any other piece. Consider, for example, the rook, who happens to be unique as well. The interesting behavior of the rook does not come from its set of movements, as it simply moves horizontally or vertically, but rather from the fact that it has the same number of moves possible from any location on the board, 14. This means that the frequency of each tile is the same everywhere, and so is the average return time, 64. Indeed, since all tiles are equally likely to be visited, then every 64 steps, you would have likely visited each tile exactly once. I hope you appreciated this video and you learned something today. To conclude this introduction on the odd game of random chess, and because we mathematicians love to ask questions, can you tell me how you expect the return time of a king to behave compared to that of the knight and the rook? We already know that the knight takes on average 168 moves to come back, and that the rook only takes 64 moves. So, is the return time of the king somewhere between these two numbers? Faster than the rook or slower than the knight? Naturally, this question can be solved with numbers and using the previous formula. But before simply computing the value, can you guess what behavior you expect in comparison to the other two? I will not be giving the solution to this problem, as you now have all the tools to do so. But if you end up computing the value, what do the numbers say? Was your instinct correct? I hope you enjoyed learning more about chess pieces randomly moving around the board. Naturally, this simple question hides a lot more than it seems, with its solution arising from properties of reversible Markov chains. But that would be for another video. Thank you very much for watching.